Our story opens in 1804 in South Wales. Cornish engineer Richard Trevithick revealed the Penydarren locomotive, the very first steam engine to ever pull a load on rails. It was a crude beast, a single horizontal cylinder driving an 8-foot flywheel, mounted on a simple 4-wheel frame, what we'd later call a Proto-040. The engine weighed about 5 tons, and on its inaugural journey it hauled 10 tons of iron and 70 passengers for 9 whole miles. But behind the triumph lay a fatal flaw. The tramroad wasn't made of steel, it was cast iron, designed for the gentle hooves of dray horses. The Penydarren's concentrated weight splintered the plates. After that one glorious journey, the locomotive was converted into a stationary engine. It didn't fail in spirit, it failed in infrastructure. 1814. From the failure of the Penydarren came a quiet revolution. 3 engineers at Wylam Colliery, William Headley, Jonathan Forster, and Timothy Hackworth, built Puffing Billy. This 040 locomotive still sits today as the oldest surviving standard gauge steam engine in the world. Weighing a little over 8 long tons, it solved the riddle of adhesion that Trevithick never cracked. Headley and his team proved that smooth iron wheels on smooth iron rails could generate enough grip, no rack and pinion needed, as long as the weight was evenly spread across the frame. Puffing Billy didn't die young. It didn't explode. It worked and worked and worked, hauling coal trucks from the pithead for an incredible 48 years, until the colliery finally retired it in 1862. Its only failure was becoming old, but in that, it succeeded more than any locomotive of its age. Jump ahead to 1829, and the world's eyes are fixed on a muddy stretch of track near Liverpool. Robert Stephenson, the son of railway pioneer George Stephenson, presented the Rocket at the Rainhill Trials, and won outright. This wasn't just a faster horse, it was the template for the next century of steam. The Rocket was a slim 022, weighing just over 4 tons. Its genius lay in the multi-tubular boiler, 25 copper tubes carrying hot gases from the firebox through the water, vastly increasing the heating surface. Combined with the blast pipe, which directed exhaust steam up the chimney to draw the fire, it hurtled along at a jaw-dropping 30 miles per hour. The engine ran in revenue service on the Liverpool and Manchester from 1830 until 1834, then had a second life in Cumberland until 1840. So why did the Rocket fail to last? It didn't fail in the dramatic sense. It was overtaken. Railway engineering was moving at rocket speed. Within a decade, its single driving axle and small boiler were outclassed by sturdier, multi-coupled engines. The Rocket was never a failure. It was the seed that grew a forest. Across the Atlantic, American ambition was on the move. On Christmas Day, 1830, the best friend of Charleston became the first U.S.-built locomotive to haul a scheduled passenger train. It was a sturdy 040, chugging along at up to 25 miles per hour on a 5-foot gauge. For 6 months, it was a celebrated success, proof that the young nation could build its own iron horses. Then, in June 1831, tragedy struck in miniature. The firemen, irritated by the loud hiss of the steam safety valve, tied the valve lever down to silence it. The boiler, with nowhere to release pressure, built up force until it exploded. The locomotive was completely destroyed, and the fireman was killed. The best friend of Charleston's career lasted just half a year. It didn't fail because of poor engineering. It failed because of a simple, stubborn human act. A powerful reminder that even the best machine is only as safe as the hands that run it. Fast forward nearly a century, and the steam locomotive had grown from a 5-ton experiment into a colossal work of art and science. In 1923, Sir Nigel Gresley unveiled the Flying Scotsman. Named after the famous London to Edinburgh Express, it was a 462 Pacific type, with 3 massive driving wheels on each side and a long, elegant boiler, weighing in at over 156 long tons. In 1934, The Scotsman became the first locomotive officially documented at 100 miles per hour, a headline-grabbing feat that made it a household name. For 40 years, it pounded the East Coast main line, pulling the most prestigious trains of the day. Why did it eventually leave service in 1963? Not because it broke, but because the world changed. Diesel electrics offered cheaper running costs and less labor, and the British Railways modernization plan swept steam away. The Flying Scotsman didn't fail. It was nudged into retirement by balance sheets, not by breakdowns. And of course, it found a second life in preservation, still steaming the rails it first graced a century ago. Gresley wasn't content with the Scotsman's success. In 1938, he took the Pacific design and wrapped it in a streamlined, powder blue casing that looked like it was doing 100 miles per hour standing still. The result was the Mallard, a 462 Class A4 weighing 165 long tons. On July 3, 1938, on a slight downhill grade at Stoke Bank, the Mallard hit an astounding 126 miles per hour, a record for a steam locomotive that has never been broken. The speed proved that well-designed, double kill-chap blast pipes and internal streamlining could push steam to its absolute aerodynamic limits. The Mallard ran faithfully for 25 years, pulling express trains on the East Coast Main Line until 1963. It wasn't a failed experiment. It was a pinnacle. When the final steam timetable was withdrawn, the Mallard went quietly into preservation, its record intact, and its heart of fire immortal. If express trains were art, American freight hauling was sheer brute force. In 1941, with war looming, the Union Pacific needed a locomotive that could drag thousands of tons over the Wasatch Mountains without a helper engine. Otto Jabelmann and the American Locomotive Company answered with the big boy. Its wheel arrangement, 4884, meant 2 sets of 8 driving wheels, articulated beneath a single massive boiler over 132 feet long. Fully loaded with coal and water, it weighed 1.2 million pounds. The big boy could produce 135,000 pounds of tractive effort, enough to start a train stretching to the horizon. 25 were built, and they pounded the rugged territory from Cheyenne to Ogden for 21 years. But all that muscle came at a price. A big boy consumed enormous amounts of coal and water, required extensive boiler washouts, and needed a full crew to maintain. When EMD's reliable diesel electrics arrived, which could be coupled together, required no ash pits, and ran with lower labor costs, the arithmetic was merciless. By 1962, every big boy was stored cold. The failure wasn't in the machine, it was in the balance sheet of the steam age. In the midst of the Great Depression, railroads needed a miracle to win back passengers from cars and planes. They found it in lightweight stainless steel and diesel-electric power. The Pioneer Zephyr, built by the Budd Company and powered by a 600-horsepower EMD diesel engine, debuted in 1934 with a record-breaking dawn-to-dusk run from Denver to Chicago. This 3-car articulated train set, with its fluted stainless steel skin and streamlined nose, looked like it had been dropped from the future. Weighing a fraction of a steam equivalent, it could hit 112 miles per hour and used incredibly little fuel. For 26 years, it crisscrossed the Burlington network, a gleaming ambassador of the diesel age. Why did it end? The Pioneer Zephyr was small. It only carried a few dozen passengers. As post-war travel boomed, the Burlington needed longer, more powerful trains. The Zephyr was gently retired in 1960 and donated to the Museum of Science and Industry, a pioneer that had successfully blazed a trail for all the diesel streamliners that followed. No crash, no explosion, simply overshadowed by the world it helped create. In the electrified Northeast Corridor, another 1934 icon was born, one with no steam, no diesel, just the silent hum of 4,600 continuous horsepower. The Pennsylvania Railroad's GG1 was a masterpiece of both mechanical and aesthetic engineering. The mechanical guts, a unique 2C plus C2 wheel arrangement with 12 driving wheels in 2 groups, were developed by Baldwin and General Electric. but the iconic welded shell with its 5 gold pinstripes was styled by Raymond Loewy, the father of industrial design. At nearly 500,000 pounds, the GG1 was heavy but graceful, capable of 100 miles per hour, and it pulled everything from the Broadway Limited to commuter locals. Its reliability was legendary. It served from the Franklin D. Roosevelt era all the way into the MTV generation, an incredible 49 years, finally retired by Amtrak in 1983. Why did the GG1 fail to reach its 50th birthday? Age, pure and simple. The frames developed cracks, the transformers contained now-banned compounds, and the newer Swedish-designed AEM-7s offered better energy efficiency. Still, a service life of half a century is anything but a failure. In 1964, as the Tokyo Olympics opened, the world discovered the future of rail was electric and ultra-fast. Hideo Shima and Shinji Sogo delivered the Shinkansen Zero Series, the first bullet train. This wasn't a locomotive with carriages. It was an electric multiple unit. Every few cars had traction motors on the axles, distributing power so evenly that a 400-meter 16-car train could accelerate smoothly and stop without crushing track. The Zero Series had a comparatively modest initial top speed of 210 kilometers per hour, but it proved high-speed rail was safe, punctual, and incredibly popular. For 44 years, the rounded nose, ivory and blue Zero Series carried millions of passengers without a single fatality from a collision or derailment. It finally bowed out in 2008, not because it failed, but because Japan had already introduced faster and quieter models with better aerodynamics and ride comfort. The Zero Series didn't crash. It faded gracefully, replaced by the technology it inspired. Its retirement was a celebration of success, not a burial of failure. The French took the baton in 1995. The TGV duplex, styled by industrial designer Roger Tallon and engineered by Alstom, tackled a very practical problem: too many passengers, not enough seats. The solution was a bi-level train that could seat 40% more people without exceeding the 17-ton axle load limit. Built extensively with lightweight aluminum, the 200-meter set weighs only 380 tons. It cruises daily at 320 kilometers per hour, and a modified version still holds the world-wheeled rail speed record at 574.8 kilometers per hour. The duplex is the antithesis of failure. It's been upgraded, re-engined, and redeployed for over 3 decades, and will likely keep running well into the 2030s. Its story isn't about why it ended, but why it refuses to end. The dawn of the new millennium brought Germany's answer to high-speed travel. The ICE-3, introduced for Expo 2000, returned to the distributed power concept. 8,000 kilowatts, over 10,000 horsepower, were packaged not in a single locomotive, but under the passenger floors throughout the entire train. This maximized passenger space, over 440 seats, and reduced axle loads. The exterior, sculpted by N+P Industrial Design, features the now famous red stripe and a sleek aerodynamic nose. 25 years later, ICE-3 units still crisscross Germany and neighboring countries, a full 3 decades of operation with no end in sight. Its story is one of evolution, not failure. 2018 marked the start of the clean energy shift on rails. Alstom's Coradia iLint is not science fiction. It's a regional passenger train running on hydrogen fuel cells, producing electricity to power traction motors, and emitting pure water vapor from the roof. The 2-car train set weighs around 72 tons, has a range of up to 1,000 kilometers, and it's now hauling paying passengers in Germany and expanding across Europe. The iLint faces no mechanical failure. Its challenge is economics and infrastructure, building enough hydrogen refueling stations to replace diesel. If it fails in the long run, it will be for logistical reasons, never for engineering ones. As of 2026, it remains a shining success. Simultaneously, in the remote Pilbara region of Western Australia, freight rail took an autonomous leap. Rio Tinto's Autohaul became the world's heaviest robot. These 2.5-kilometer-long trains, weighing up to 30,000 tons, snake through the red desert with no driver on board. The locomotives respond to a central command in Perth, 1,500 kilometers away, using automatic train operation systems. There's no crew change, no hours of service limit, just efficient, relentless hauling. Failures here are measurable in milliseconds of latency. Reliability is above 99.9%. The autohaul hasn't failed. It's redefined what rail freight means. Finally, at the outermost edge of rail science, Japan's L0 series Maglev floats above the track. There are no wheels, no pantographs touching a wire. Superconducting magnets cooled to minus 269 degrees Celsius create a levitation force that lifts the train 10 centimeters and propels it silently at over 500 kilometers per hour. In 2015, a 7-car L0 set hit 603 kilometers per hour, a world record for any train. The 15-meter aerodynamic nose is engineered to reduce the tunnel boom, the shockwave that would otherwise burst out of tunnel exits. The train is technically a success. Its potential failure lies in the staggering $100 billion price tag of the Choshinkansen line and the years of tunnel excavation still ahead. But if Japan succeeds, the L0 will be the fastest, most remarkable train in the history of human mobility.